Day 1, the Rust toolchain and your first program. You have heard that Rust is fast, that it is safe, and that its compiler is strict to the point of being a personality. Today you find out what all three really mean by installing the toolchain, building and running your first program, reading your first compiler error, and meeting Tally, the small data tool you will grow into a real application over the next 3 weeks. Today you will install Rust with RustUp and create a project with Cargo. Write and run a program that prints with println. Read your first compiler errors and fix them. Meet Tally, the data tool you grow across the book. Why Rust and why now? Most languages ask you to choose. You can have the raw speed of C and C++ and accept that a single careless pointer can corrupt memory and crash in production. Or you can have the safety of a garbage-collected language like Python, Java, or Go and accept the runtime cost and the pauses that come with it. Rust's whole reason for existing is to refuse that trade. The two promises, speed and safety. Rust makes two promises at once. The first is performance. Rust compiles to native machine code with no interpreter and no garbage collector, so a well-written Rust program runs as fast as the equivalent C. The second is safety. The compiler proves, before your program ever runs, that it is free of whole categories of bugs, dangling pointers, use-after-free data races, that have caused decades of crashes and security holes. The surprising part is that you do not pay for the second promise with the first. There is no runtime garbage collector scanning memory, no reference counting on every value, no virtual machine. The checks happen at compile time and then disappear. The machine code Rust emits looks like the machine code a careful C programmer would write. It is just that the compiler has already checked the things the C programmer had to remember by hand. Where Rust came from and why it caught on. Rust began as a personal project at Mozilla and grew into the language that now powers parts of Firefox, Windows, the Linux kernel, Dropbox, Cloudflare, and the infrastructure behind countless web services. For several years running, it has topped the survey of the language developers most want to keep using. That popularity is not hype for its own sake. It comes from the daily experience of shipping code that simply does not have the bug you were dreading. What changed recently is that the ecosystem grew up. The package manager, the editor support, the libraries for web servers, command line tools, and embedded devices are now mature. Learning Rust in 2026 means learning a language that is stable, well-documented, and in demand, not a research experiment. There is also a quieter reason Rust spread so fast. Teams that adopt it report a particular kind of relief. Whole categories of bug, the seg fault, the Heisenbug that only appears under load, the security advisory about a buffer overrun simply stop happening. Microsoft and Google have both reported that the majority of their serious security vulnerabilities came from memory bugs of exactly the kind Rust prevents, and both have begun rewriting critical components in it. You are not learning a niche curiosity. You are learning a language that large engineering organizations are betting their most sensitive code on. What you get on day 1. When you install Rust, you do not just get a compiler. You get a build system, a package manager, a code formatter, a linter, and a documentation generator, all designed to work together. By the end of today, you will have used the first few of these tools to create, build, and run a real project, and you will understand the pieces well enough to keep going on your own. This integrated toolchain is part of why Rust is pleasant to learn. In some languages, getting from installed to running my first program means choosing a build tool, a package manager, and a project layout, then wiring them together. In Rust, those choices are made for you, and they are good choices, shared by the whole community. The result is that a Rust project you download from anyone in the world looks like a Rust project you would write yourself. Same layout, same commands, same conventions. You learn the workflow once, and it serves you everywhere. Figure. A diagram placing programming languages on two axes, runtime speed and memory safety, with C and C++ fast but unsafe, scripting languages safe but slow, and Rust alone in the fast and safe corner. What safe systems programming means. The subtitle of this book is a hands-on course in safe systems programming. Each of those words carries weight, and understanding them now will tell you what kind of language you are about to learn. Systems programming, briefly. Systems programming is writing the software that other software runs on. Operating systems, databases, browsers, game engines, network services, command line tools, and embedded firmware. It is the world where performance and control matter, where you care how memory is laid out, how many allocations you make, and how close to the hardware you can get. Traditionally, this has been the domain of C and C++, because they give you that control. Rust gives you the same control without the same danger. Memory safety is the guarantee that a program never reads or writes memory it does not own. No dangling pointers, no buffer overruns, no use after free, no data races. Rust enforces memory safety at compile time for code outside an explicit unsafe block. The bugs the compiler refuses to ship. In C and C++, the most dangerous bugs are not logic mistakes, they are memory mistakes. You free a buffer and then use it again. You hold a pointer to something on the stack after the function returns. Two threads write the same variable at once. These bugs are hard to reproduce, hard to find, and behind a large share of the security vulnerabilities reported every year. Rust's compiler rejects these programs. It tracks who owns each piece of memory and how long each reference is allowed to live. And if your code could possibly read freed memory or race on shared data, the program does not compile. This is jarring at first. The compiler tells you no a lot in week 1, but it is the same no that would otherwise have been a 2 a.m. Production page. Consider the most infamous example. In C, you can free a block of memory and then keep using the pointer to it, a use after free. The program might appear to work, because the freed memory has not yet been reused, and then crash unpredictably weeks later when it has. Whole classes of security exploits are built on exactly this gap between freed and noticed. Rust closes the gap by construction. Once you give up ownership of a value, the compiler will not let you touch it again, and it knows at compile time precisely when each value is freed. The bug is not caught by a test or a tool you have to remember to run. It is simply not expressible in safe Rust. Safety without a garbage collector. Other safe languages achieve memory safety with a garbage collector, a runtime component that periodically finds memory no longer in use and frees it for you. It works, but it costs CPU time and introduces unpredictable pauses, unacceptable for an operating system kernel or a high-frequency trading system. Rust takes a different path. It decides at compile time exactly when each value is created and destroyed, using a system of ownership you will meet on day 4. There is no runtime collector because there does not need to be one. The cleanup code is built into the program at compile time, exactly where it belongs. This is the idea Rust people call zero-cost abstraction. You write code at a high level, collections, iterators, safe references, and the compiler turns it into machine code with no overhead you did not ask for. The safety checks live entirely in the compiler and leave no trace in the running program. A Rust program does not carry a garbage collector, a runtime, or hidden bookkeeping. It is as lean at runtime as the C you would have written by hand, but the compiler has already proven the things you would have had to keep in your head. You get the high-level convenience and the low-level performance at once, which is the whole promise restated in 3 words. Figure. A shield labeled the borrow checker, stopping 4 classic memory bugs from reaching production. Use after free, dangling pointer, buffer overrun, and data race, each shown as an arrow blocked at compile time. Note: you will spend days 4 and 5 on ownership and borrowing, the heart of how Rust delivers safety without a garbage collector. For now, just hold on to the idea that the compiler is tracking memory for you, and the strictness you feel early on is that tracking at work. Installing Rust with RustUp. Before you can write Rust, you need the toolchain. The official, recommended way to get it is RustUp, a small program that installs and manages everything else. RustUp, the toolchain manager. RustUp is not the compiler. It is the tool that installs the compiler and keeps it up to date. It can hold several versions of Rust side by side, stable, beta, nightly, and switch between them per project. For this book, you want the stable toolchain, which is what RustUp installs by default. When people say install Rust, they almost always mean run RustUp. It works the same way on Windows, Mac OS, and Linux, and it installs everything into your user account, so you never need administrator rights. The reason RustUp manages versions rather than just installing one is that Rust releases a new stable version every 6 weeks, like clockwork. Keeping current is a single command, RustUp update, which fetches the latest stable toolchain and leaves your projects working. The addition system guarantees old code keeps compiling. Most of the time, you will install once today and forget RustUp exists until you want to update. But it is quietly doing important work, pinning a known compiler version, fetching extra components when you need them, and letting an advanced project request a specific toolchain without disturbing your defaults. Installing on Windows, Mac OS, and Linux. On Mac OS or Linux, open a terminal and run the one-line installer from the official site. Installing Rust on Mac OS or Linux. The code is shown in the book. On Windows, download and run RustUp in it, exe from RustUp, RS, or install it with the System Package Manager. Installing Rust on Windows with Winget. The code is shown in the book. Accept the default installation when prompted. On Windows, Rust uses the Microsoft Visual C++ build tools for linking. If RustUp tells you they are missing, it will point you to the small installer you need. What you just installed. When RustUp finishes, you have 4 tools on your path. Confirm them. Checking that the toolchain is installed. The code is shown in the book. Rust is the compiler, Cargo is the build tool and package manager, and RustUp also installed Clippy, a linter, and rustfmt, a formatter that you will meet later. If both commands print a version, you are ready. You also got the documentation. Rust ships its entire reference and standard library docs to your machine, so you can read them with no network connection at all. Opening the local documentation. The code is shown in the book. This opens the standard library documentation in your browser, the same pages you will return to constantly as you learn your way around STD. It is worth bookmarking now. The Rust community treats documentation as a first-class part of the language, and you will find that even third-party libraries you install later come with thorough, searchable docs generated by the same tool. Figure. A layered diagram showing RustUp at the top managing a stable toolchain, which contains 4 tools beneath it. Rust the compiler, Cargo the build tool, Clippy the linter, and rustfmt the formatter. Tip. If you installed Rust and the Cargo command is not found, you almost certainly need to open a new terminal so it picks up the updated path. The installer adds Rust to your path, but already open shells do not see the change. Cargo, build, run, and project layout. You could call Rust directly on a single file, and on day 1 that even works. But real Rust projects are built with Cargo, and you should start as you mean to go on. Creating a project with Cargo new. Cargo creates, builds, tests, runs, and packages your code, and fetches the libraries you depend on. Make your first project with one command. Creating a new project. The code is shown in the book. Cargo new hello makes a folder called hello, containing a complete, ready-to-run project. The word binary means this project builds into an executable program, as opposed to a library, which is code other programs use. The files Cargo made. Look at what Cargo created. The files in a new Cargo project. The code is shown in the book. Cargo toml is the project's manifest. Its name, version, and list of dependencies, written in the TOML format. src/main. rs is your source code, and Cargo has already filled it with a working hello world program. Everything you write goes under src/. Cargo also initialized a Git repository in the folder and added a git ignore that excludes target, so your project is ready for version control from the first second. This is the convention over configuration philosophy at work. Rather than make you decide where source lives, how to ignore build artifacts, and how to lay out a project, Cargo picks sensible answers that the entire Rust world shares. The payoff is consistency. Open any Rust project, and you already know that the manifest is Cargo. toml, the code is under src/, and the build output is in target. The generated Cargo toml. The code is shown in the book. The addition line is worth noticing. Rust evolves in additions, 2015, 2018, 2021, that let the language add features without breaking old code. This book targets the 2021 edition, which is what Cargo selects for you. Cargo run and the target directory. Now build and run it with a single command. Building and running the project. The code is shown in the book. Cargo run compiled your code, placed the resulting executable in a new target directory, and then ran it. You will see target appear in every project. It holds build output and is safe to delete at any time. Cargo just rebuilds it. It is also the one folder you never check into version control. Cargo also created a cargolock file the first time it built. Where Cargo, toml records the dependencies you asked for, often as flexible version ranges. Cargolock records the exact versions Cargo actually chose, so that everyone who builds your project gets identical dependencies down to the patch number. You rarely edit it by hand, Cargo manages it, but it is why a Rust project that built for you will build the same way for a teammate a year later. The same Cargo command is also how you will run tests, Cargo test, format code, Cargo fmt, lint it, Cargo clippy, and eventually publish a library, all of which you will meet in the weeks ahead. Figure. A file tree panel of a new Cargo project showing cargo.toml as the manifest, the src folder containing main.rs, and a grayed-out target folder labeled build output, safe to delete. Hello world with println. You have already run a hello world. Now let us read it, change it, and understand the one piece of magic it contains. Your first program. Open src/main, rs. Cargo put exactly this in it. The generated main, rs. The code is shown in the book. 3 things are happening. fn main declares a function named main. The curly braces hold its body. And the one line inside prints text to the screen. Change the message, save the file, and run Cargo run again to see your new text appear. That edit save run loop is the heartbeat of learning Rust, and it is worth doing literally right now rather than reading on. Change hello world to a sentence of your own, run it, and watch your words come back. The loop is fast and forgiving. There is nothing you can type into this program that will harm anything, and the worst case is a compiler error that tells you exactly what to fix. Every concept in this book is best met the same way: change the listing, predict what will happen, run it, and find out whether you were right. Println is a macro, not a function. Notice the exclamation mark in println. That is not decoration. It tells you that println is a macro, not an ordinary function. A macro is code that writes code. It runs at compile time, expanding into ordinary Rust before your program is built. Rust marks macro calls with a trailing, so you can always tell them apart from function calls. Println is a macro because it does something a normal function cannot. It checks your formatting string against its arguments at compile time. If you ask it to print a value you forgot to supply, the error appears when you build, not when you run. Printing values and formatting. Println can interpolate values into a template using curly braces as placeholders. Printing values with placeholders. The code is shown in the book. You can name the value directly inside the braces, when it is a simple variable, or leave the braces empty, and pass the value as an argument after the string. Running this prints 2 lines, with the values slotted into place. There are 2 more printing tools you will reach for constantly. Print no ln prints without a trailing new line, and the placeholder prints a values debug form, a developer-facing representation that works for many types, including ones that have no normal text form. Debug formatting and printing without a new line. The code is shown in the book. The placeholder asks for the debug form, which prints the tuple as 1, north. You will lean on heavily while learning, because it lets you peek at almost any value, a vector, a struct, an error, without writing display code first. When you build your own types later, deriving debug formatting is a single line, and from then on they print 2. Figure. A fake terminal panel showing the command cargo run, followed by the compiler progress lines and the program output greeting rustation and the year, with the placeholders highlighted to show where each value was inserted. Tip. The word rustation is what Rust programmers call themselves, and the unofficial mascot is a small crab named Ferris. You will see crabs in the Rust community everywhere. Now you know why. Anatomy of a Rust program. That tiny program already shows most of the shape every Rust program shares. Let us name the parts so the larger programs ahead feel familiar. Main, where execution begins. Every executable Rust program has exactly one function named main, and that is where execution starts. When you run the binary, Rust calls main. When main finishes, the program ends. You can define as many other functions as you like, but main is the front door. The fn keyword declares a function, followed by its name, a pair of parentheses for its parameters empty here, and a body in curly braces. You will write many functions, they all follow this shape. Unlike scripting languages, Rust does not run loose code at the top of a file. There is no module body that executes line by line. Everything happens inside a function, and the program starts at main. This is part of why Rust programs are predictable. There is exactly one entry point, and the path from there is explicit. When main returns, the program is over, and Rust runs the cleanup for every value still alive, closing files, freeing memory automatically, and in a defined order. You will see on day 4 that this orderly shutdown is the visible tip of the ownership system. Statements, expressions, and the semicolon. Inside the body, each step usually ends with a semicolon. In println, hello, world, the semicolon marks the end of the statement. Rust cares about the difference between a statement, a step that does something, and an expression, a piece of code that produces a value more than most languages do, a distinction you will use heavily on day 3. For now, notice that lines that do something end in a semicolon. This distinction has real consequences you will appreciate later, so it is worth seeing once now. In Rust, an if, a block in curly braces, and even a match are expressions, they produce a value, which means you can assign their result directly to a variable. Most C-family languages treat these as statements and force you to write to the variable from inside each branch. Rust's view is more uniform. Code either is a value or does something, and the semicolon is how you turn the first into the second. You do not need to master this today. Just file away that the humble semicolon carries more meaning here than you are used to. A function body is a sequence of steps. The code is shown in the book. Comments and the shape of the code. Anything after on a line is a comment, ignored by the compiler, there for human readers. Rust also uses indentation of 4 spaces per level by convention, and Rust font will enforce it for you so you never have to think about it. Figure. An annotated panel of a small Rust program labeling the fn keyword, the function name main, the parameter list, the body in braces, a let statement, a macro call, and a line comment, so each part of the syntax is named. Note: Rust does not care about most whitespace. It uses braces, not indentation, to group code. But idiomatic Rust is always for space indented and formatted by Rust font, so your code looks like everyone else's and is easy to read. Crates, the standard library, and the prelude. Where did println come from? You did not define it, and you did not import anything. The answer introduces 3 words you will use constantly: crate, standard library, and prelude. Crates, the unit of Rust code. A crate is the unit of compilation in Rust, a single library or executable that the compiler builds as a whole. Your Hello project is a crate. Every library you depend on is a crate. When you build a project, Cargo compiles your crate together with all the crates it depends on. The website Crates.io is the public registry where Rust libraries are published. Adding one to your Cargo, TOML is all it takes to pull it into your build. You will do exactly that on day 8. There are 2 flavors of crate, and the difference matters. A binary crate compiles to an executable you can run. It has a main function, and hello is one. A library crate has no main. It is code meant to be used by other crates, like the standard library or anything you download from crates.io. As Tally grows, you will actually split it into both: a library crate holding the logic and a thin binary crate that wires up the command line. That split is what lets the same code be tested in isolation and reused, a pattern you will set up on day 8 and rely on for the rest of the book. The standard library and STD. Rust ships with a standard library, known in code as STD. It provides the fundamental building blocks: text handling, collections like growable arrays and hash maps, file and network input and output, threads, and much more. Unlike a dependency from Crates.io, STD is always available. It comes with the compiler. Println lives in STD. So does the string type, the vec growable array, and the result type you will use for error handling. A large part of learning Rust is learning your way around the standard library, and this book introduces its most important pieces as you need them. When you need something from STD that the prelude does not bring in automatically, you pull it into scope with a use line at the top of your file. Bringing an item into scope with use. The code is shown in the book. The hash map type, a dictionary mapping keys to values, lives in STD. Collections, which is not in the prelude, so you name its path once with use and then refer to it by its short name. You will write many use lines, and on day 8 you will see how the same mechanism organizes your own code into modules. For now, the takeaway is simple. Everything in STD is available, and use is how you reach the parts the prelude leaves out. The prelude, what you get for free. You did not have to write use STD, println to call println, and you will not have to import the most common types either. That is because of the prelude, a small set of the most used items that Rust automatically brings into scope in every program. The prelude is why string, vec, option, and result just work without ceremony. Figure. 3 nested boxes showing your crate at the center, surrounded by the standard library STD, with a small highlighted ring labeled the prelude, marking the handful of items imported automatically into every program. Compiling, linking, running. You have been typing cargo run and watching output appear. Underneath, several steps run in order, and knowing them makes the rest of your work faster. From source to running binary. When you run cargo run, Cargo invokes Rust, the compiler on your source. Rust checks your code, translates it to machine code, and links it, combines it with the standard library and any dependencies, into a single executable file in target. Then Cargo runs that file. The whole pipeline is automatic, but each stage can fail independently, and the error messages tell you which stage you are in. Figure. A pipeline diagram showing source code flowing into Rust, which checks and compiles it, then links it with the standard library into an executable in the target folder, which is then run to produce output. Cargo check, the fast feedback loop. Compiling all the way to a runnable binary takes time. Often you just want to know, does this compile? And for that, there is a faster command. Checking code without building a binary. The code is shown in the book. Cargo check runs the compiler's analysis, all the type and borrow checking, but stops before generating the final machine code. It is dramatically faster than a full build, and during development, you will run it constantly to catch errors the moment you make them. Tip: get in the habit of running cargo check after every few edits. It gives you the compiler's verdict in a fraction of the time of cargo run, and catching an error one line after you wrote it is far easier than catching it 10 edits later. Debug versus release builds. By default, cargo builds in debug mode, fast to compile with extra checks but not optimized for speed. When you are ready to measure performance or ship, build in release mode. Building an optimized release binary. The code is shown in the book. A release build can be many times faster at runtime than a debug build because the optimizer is turned on. The trade-off is a slower compile, which is why you keep debug mode for day-to-day work and switch to release only when speed matters. The gap between the two modes is not small. A number crunching program can run 10 or more times faster in release mode. Debug mode also keeps extra safety checks turned on. For instance, arithmetic that overflows an integer will panic and stop the program in debug, where release mode wraps around silently for speed. You will meet this exact behavior on day 2. The practical rhythm is: develop and test in debug, where compiles are fast and checks are loud, and build with release whenever you measure performance or hand the program to someone else. Cargo keeps the two builds in separate folders under target, so switching between them never forces a full rebuild of the other. Reading Rust compiler errors. Here is the skill that separates people who enjoy Rust from people who fight it. Reading the compiler's errors as help, not as rejection. Rust's error messages are among the best of any language, and they are trying to teach you. Errors are a feature, not a wall. In week 1, the compiler will reject a lot of your code. This is the language doing its job. Every no is a bug it caught before your users could. The messages are written to be read. They tell you what went wrong, point at the exact spot, and very often suggest the fix. It helps to reframe what is happening. In a language that compiles loosely and crashes at runtime, the compiler is a gate you rush through, and the real feedback comes later, from a user or a crash log. In Rust, the compiler is a pair programmer who reviews every line before it runs. The conversation feels slow at first because you are having it now instead of at 2 a.m. Next month, but it is the same conversation. Move to the cheapest possible moment to have it. Once you internalize that, the red text stops feeling like failure and starts feeling like the fastest code review you will ever get. Anatomy of an error message. Make a deliberate mistake to see one. Change the program to use a variable you never declared. A program with a deliberate error. The code is shown in the book. Building it produces. The compiler's error message. The code is shown in the book. Read it top to bottom. Error 0425 is a stable error code you can look up. The plain English line says what is wrong. Cannot find value count in this scope. The arrow points at the file, line, and column. And the underlined span shows you exactly where. Nothing here is mysterious once you slow down and read it. The error code in the brackets is more than a label. It is a key into a built-in encyclopedia. Run Rust explain E425, and the compiler prints a page-long explanation of that whole category of error, with examples of code that triggers it and code that fixes it. When a message is not enough on its own, that command almost always is. And when an error spans several lines or several files, Rust shows each relevant location with its own arrow and span, so even a complex mistake is laid out as a connected story rather than a single cryptic line number. Figure: an annotated compiler error message labeling its 4 parts. The error code in brackets, the human-readable description, the file and line location after the arrow, and the underlined span pointing at the exact problem in the source. Fixing a real error. The fix is to declare count before you use it. The corrected program. The code is shown in the book. Many Rust errors go further and print a help line with the exact change to make. Sometimes you can almost fix the code by typing what the compiler suggests. Learning to read these messages is the single highest leverage habit you can build this week. Warning: resist the urge to guess randomly when the compiler complains. Read the whole message first, the description, the location, and any help line. Rust's errors are detailed on purpose. Skimming them and changing code at random turns a 5-second fix into a long, frustrating loop. The project you will build, Tally. You will not learn Rust by reading about it. You will learn it by building one real program, a little more each day, until you have an application worth keeping. That program is Tally. Meet Tally. Tally is a command-line data tool. You feed it records, rows of comma-separated values, like a spreadsheet exported to a text file or a server's log, and it filters them, adds them up, summarizes them, and prints a report. It is small enough to understand completely and real enough to exercise the whole language. This kind of tool is the perfect vehicle for learning Rust because it touches every part of the language naturally. Reading a file is input and output. Splitting a line into fields is text handling and slices. Deciding whether a field is a number, a word, or empty is enums and pattern matching. Holding the rows in memory is ownership and collections. A bad line in the input is error handling. Adding up a column is iterators. Scanning many files at once is concurrency. You will not have to invent contrived exercises to practice each concept. The next feature Tally needs will be exactly the concept the day taught, every day, for 3 weeks. A taste of the data Tally works with. The code is shown in the book. What Tally will do by day 21. By the end of the book, Tally will read records, select the ones you care about, compute statistics, and print formatted reports. From the command line, fast. Here is a session with the finished tool, so you know where you are headed. The finished Tally in action, day 21. The code is shown in the book. Every feature in that session, reading a file, parsing numbers, grouping, aggregating, formatting, is a Rust concept you will learn and then apply the same day. Figure: a pipeline diagram of the Tally tool showing records flowing in from a file, through a filter stage that keeps matching rows, into an aggregate stage that computes counts and sums, and out to a report stage that prints a formatted table. How the project grows with you. You will not build Tally all at once. Each day's final section adds one piece using the concept you just learned. Day 4 makes Tally own its data correctly. Day 7 models a record with an enum. Day 10 gives it real error handling. Day 14 builds its query pipeline from iterators. Day 18 scans many files in parallel. By day 21, the pieces assemble into the finished tool, and you will have learned the language by building something with it. How this book works. You now have the toolchain, a running program, and a goal. A word on how the next 20 days are organized will help you get the most from them. The daily rhythm. Each day is one chapter you can finish in a sitting, and every chapter has the same shape. It opens with what you will be able to do by the end. It teaches through short sections, each introducing one idea, showing it in runnable code, picturing it in a figure, and reinforcing it with a note or a tip. Every day closes with a summary, a short questions and answers, and a workshop of quiz questions and hands-on exercises. The 3 weeks build on each other. Week 1 is the language core and the ownership model that makes Rust Rust. Week 2 is abstraction, modules, collections, error handling, generics, traits, lifetimes, and iterators. Week 3 is the standard library, concurrency, async, and finishing Tally into a shippable tool. Because each day builds on the last, the order matters. Work through the days in sequence rather than skipping ahead. A concept introduced on day 7 assumes you met the one from day 4, and tally on day 14 assumes the version you left on day 10. If you have programmed before, some early material, variables, loops, functions will feel familiar, and you can move through it quickly. But read it, because Rust gives even familiar ideas its own twist, and those twists are where the surprises hide. The goal is not to finish fast. It is to reach day 21 able to read, write, and reason about real Rust with confidence. How to read the listings and figures. The code in this book is meant to be typed, not skimmed. Every listing is real Rust you can put in src/main, rs, and run. Type it yourself rather than copying it. The muscle memory of writing a match, a struct, or an iterator chain is worth more than reading 100. The figures picture the ideas the prose describes. Glance at each one when you reach it. When a listing does not compile for you, that is a feature of the process, not a setback. Read the error, fix it, and you have just practiced the most important Rust skill there is. Some listings in this book are meant to fail, to show you what a particular mistake looks like. Those are always clearly labeled, and the corrected version follows. New terms appear in boxes the first time they matter, and short notes, tips, and warnings sit alongside the prose to flag the thing that will trip you up or the shortcut worth knowing. None of it is decoration. All of it is there because someone learning Rust needed exactly that reminder at exactly that spot. What you need and how to get unstuck. You need the toolchain you installed today and a text editor. Any will do, though an editor with the Rust Analyzer extension will underline errors as you type and is well worth setting up. When you get stuck, the official documentation is excellent. Rust Explain E425 expands any error code, and the standard library docs are a command away with rustup.doc std. Figure. A roadmap of the 21 days arranged as 3 weeks, the first labeled core language and ownership, the second abstraction generics and errors, the third standard library concurrency and capstone, with tally growing across all 3. Tip. Keep a Scratch project open in a second terminal while you read. When a listing introduces something new, paste it in, run it, and change one thing to see what happens. The fastest way to learn Rust is to argue with the compiler about small programs. Summary. Today you met Rust, a language that delivers the speed of C and the memory safety of a garbage-collected language at the same time, by doing its safety checking at compile time instead of with a runtime collector. You learned that safe systems programming means writing the fast, low-level software that other software runs on, without the memory bugs that have haunted C and C++ for decades. You installed the toolchain with rustup, which gave you the compiler Rust, the build tool cargo, and the linter and formatter you will meet later. You created a project with cargo new, learned the layout cargo makes cargo, toml for the manifest, src/main, rs for your code, target for build output, and built and ran it with cargo run, with cargo check as your fast feedback loop. You wrote and changed a program that prints with the println macro, learned why it's marks it as code that writes code, and saw how curly brace placeholders interpolate values. You named the parts of a Rust program, main as the entry point, statements ending in semicolons, the crate as the unit of compilation, and the prelude that imports the common types for free. Most importantly, you read your first compiler error and saw that its 4 parts, code, description, location, and span, are there to help you, not to stop you. Finally, you met Tally, the command line data tool you will grow across the book, and saw the finished tool you are working toward. Tomorrow you start filling it in, beginning with how Rust stores values, variables, types, and mutability. Questions and answers. Q. Do I need to know C or C++ before learning Rust? A. No. You need to be comfortable programming in some language, variables, functions, loops, conditionals, but you do not need any systems programming background. This book builds Rust and the ideas behind it like ownership, from the ground up. Knowing C can help you appreciate why Rust does some things, but it is not a prerequisite. Q. Why does the compiler reject so much of my code at first? A. Because it is checking things other languages leave to runtime or to you. Most early rejections are about ownership and borrowing, the rules that guarantee memory safety. The strictness front-loads the pain. You argue with the compiler now instead of debugging a crash later. By week 2, the rules feel natural, and the rejections become rare and informative. Q. Should I use cargo run or call Rusk directly? A. Use cargo. You can compile a single file with Rusk main, rs, and it works for tiny experiments, but every real project uses cargo for building, testing, dependencies, and packaging. Starting with cargo now means nothing to relearn later, and it is barely more typing. Q. What is the difference between cargo check and cargo build? A. Cargo check runs the compiler's analysis, type checking, borrow checking, all the error detection, but stops before generating the final machine code, so it is much faster. Cargo build and cargo run goes all the way to a runnable executable. Use check constantly while writing, and build or run when you actually want to run the program. Q. What does the in println mean? A. It marks println as a macro rather than a function. A macro expands into code at compile time, which lets println check your format string against its arguments before the program runs. Anytime you see a trailing. On a call, you are calling a macro, not an ordinary function. Q. Is it safe to delete the target directory? A. Yes, always. Target holds nothing but build output. Compiled artifacts cargo regenerates from your source. Deleting it just means the next build starts from scratch. You should never commit target to version control. A new project's gitignore excludes it for you. Workshop. Quiz. In one sentence, what are the two promises Rust makes that most languages force you to choose between? What does memory safety mean, and at what point, compile time or runtime, does Rust enforce it? Name the 4 tools RustUp installs, and say what each one does. What 3 things does cargo new create, and what is each one for? Why is println written with an exclamation mark, and what does that mark tell you? Name the 4 parts of a Rust compiler error message, and what each part tells you. Exercises. Install and verify. Install Rust with RustUp if you have not, then run Rusk version and cargo version in a fresh terminal and confirm both print a version. Write down the version numbers you got. Make and run a project. Use cargo new to create a project called greeter. Change the message in src/main. rs to greet you by name and run it with cargo run. Then run cargo run release and note how the output line differs. Print with placeholders. Rewrite main so it declares 2 variables, your name and your favorite number, and prints a single sentence that uses both, once with a named placeholder and once with an empty placeholder and a trailing argument. Read an error on purpose. Delete a semicolon or misspell a variable name, run cargo check, and read the full error message. In one sentence each, identify the error code, the description, and the location it reports, then fix the code. Explore an error code. Take the error code from the previous exercise and run Rusk explain followed by that code. Read the explanation and write one sentence on what category of mistake that code covers.